Actually, he said yesterday his part of job was missing, and today I kept it here and it's
Let's get started. If you will continue the lectures on the single Levi-flat hypersurfaces.
Right. So, what I want to prove, I need to build up some lemmas, but I want to prove that locally all non-singular Levi-flat hypersurfaces, real-algebraic, are basically the model one that we were given. So for that, we need to introduce CR functions. So functions that satisfy the tangential Cauchy-Riemann on a manifold, because we'll need to talk about extending them. Because if we want to, if we're going to want to flatten these Levi-flats, what we'll want to do is we want to define the new coordinates intrinsically and then extend them to get nice ambient new coordinates. So suppose that you have, so at this point, just any hypersurface, a CR manifold, define CR manifolds. So and the hypersurface in Cn, then function f. I mean, at least as I said, the worst regularity I'll smooth. So a smooth function is CR if just like for holomorphic function, if I'll write maybe CR vector fields as just be a little bit more consistent. So if I have X were the CR vector fields, then maybe I'll say X bar are the 0, 1 vector fields. So if this 0 for all, let me write it like this: X for all sections of 0, 1. So whenever you have 0, 1 vector field, it kills F. Right. So exactly the way that you would do holomorphic functions. M with Cn, this would be precisely holomorphic functions. All right. So these are the generalization of holomorphic functions, because if let's just suppose something simpler. Let's suppose that I have maybe holomorphic in Cn. It doesn't have to be in Cn. It could just be in some neighborhood of n. Then capital F restricted to M is CR. Why is that? Well, if I have that's basically this idea of these vector fields. Like these are the tangential vector fields, but we can I could just if I write them in the extrinsic coordinates, I'm going to have some set of 0, 1 vector fields on Cn. Maybe not going to be all of them, but I can then complete the basis to get all of them. Right? And these are so they're really coming from there, and these are specifically the ones that are tangent. So the only ones that I can differentiate this guy with, right? So so this guy is skilled by all the 0, 1 vector fields. So it's in particular going to be killed on M by the ones that are tangent to M, because it's actually killed by a lot more, right? So this is definitely true. If I have a holomorphic function, again, it could be just some neighborhood of M. It doesn't have to be Cn. Then I have a CR function. The vice versa is more complicated. So let's suppose that M is given by, suppose it is this. You could just think in one variable if you have W as our only variable. If I have this M, this model Levi-flat, or in one variable just the real line, then I could take basically any smooth function in W, right, or in the real part of W, and I'm gonna have a function which cannot possibly extend unless it is real-analytic, because if it extends, M is real-analytic. So if I put real-analytic coordinates on M, which would be, let's just stick to, like, let's suppose it is actually in C, right? Then I would plug in real W would be my coordinate. I plug that into my and that's a real-analytic sort of coordinates. I plug it into my holomorphic functions. I get a real-analytic function. So if it's smooth but not real-analytic, then it cannot possibly extend. For example, I could let, again, just on M, right? Just think of it as a function of real W, right? Standard maybe. Right now, there's only one word. So that would be just the standard. This is not real-analytic, so this cannot possibly extend. It is CR, right? Even if we think of this in Cn, because it doesn't depend on any of the z's. And if you remember, the CR vector fields over here, we're just in the z's, right? So I guess the 0, 1 vector fields would be in the z bars, right? And so I differentiate with respect to z bars. Well, there's no z's, right? So it's just 0. It doesn't depend on those variables, right? So this is definitely CR, but it cannot possibly be a restriction of a holomorphic function. So for smooth, it's generally not true that you can extend, and it's generally not even, well, I guess maybe it's sometimes possible to extend to one side, maybe kind of actually generically, but in the Levi-flat case, no. So in this case, this guy doesn't even extend to either side. You cannot have it be a boundary value of a holomorphic function. But it's maybe not too important.
Extending the sense of holomorphic.
Yeah, holomorphic. So if I have a holomorphic function with boundary value on M, so on one side of M, maybe I would get a holomorphic function whose boundary value would be this. That's one actually not.
Just the function real W to the power square.
Yeah, so it's not possible. Right.
Just a function real to the power W, real of W plus square.
Well, so this thing, right? But that's not going to be nice and continuous up to, right? So it's not going to have a nice boundary value, right? I mean, that is the obvious extension, right? I mean, you could think of it. Let's maybe, off of so even on just one side, maybe on the upper half plane, right? I could just think of this function, right? Which is going to on M it's going to equal this. It's not going to be continuous up to the boundary. It's going to blow up. Right, and it blows up from either side, right? And this by identity theorem, that's the only possibility. So you cannot extend even just to one side, but definitely not to both sides. All right. So the question is, if we can do this, if we have something nicer. So as I said, if we have a real-analytic manifold. And it's a restriction of a holomorphic function. Well, if I have real-analytic coordinates, I plug them in to the holomorphic function. It's clearly real-analytic. So does it go the other way? Is it true that whenever I have a real analytic CR function, is it necessarily a restriction of a holomorphic function? And the answer is true. It's yes. And it's basically this just a generalization of basically this the sort of the standard one variable thing where you have something on the real line and you're complexifying it, like you're computing contour integrals, right? It's a standard thing. It's you have something in terms of a real variable, you consider it a complex variable, right? It's the same idea, but it's a little bit more intricate, because in one variable, you can think of, if I have a hypersurface, there's no CR vector. So every, if I'm on the real line, right here, if I'm on the real line, right, just in C, there's there's no CR vector. This is a hypersurface, and any function on here is a CR function, right? And so any real analytic function will extend, and really the way it is, like if I'm at 0, if I have power series, I just start plugging in complex numbers for x, and then that will agree. And if this power series converges in some neighborhood, I should go and converge in a disk and so on, right? So there's no problem in one variable, but that's not quite easily going to work in several variables because of this CR thing, right? Just getting some. So if I have, it's not hard to get some extension, again, just by plugging in. I have real power series. I can just start plugging in complex numbers, right? So that works, but I'm not going to necessarily get because in the real power series, really what I need to do is write it in terms of the Z's and Z bars, and I'm not necessarily going to get a nice holomorphic function. I might get a holomorphic function, let's say, of two variables, Z and Z bars, separately, but not necessarily just of Z, because that would require the Cauchy-Riemann equations, right? So I have to somehow make sure that if I do this extension, which gives me too many variables, that I can say, well, the other variables aren't really there if I have a CR function. That's going to be basically the idea, right? And if I don't have a CR function and the other variables are there, I just have basically a real analytic function written in weird coordinates. So the main idea of this is complexification. And so maybe let me just for notation, if I have this multi-index notation, but I'm going to want to use it. Let me be more precise. If I have this multi-index, and so last time, first time, I have single monomial. That's what I mean. But I can apply this to not just monomials, but also the derivatives. So I can take the alpha's derivative with respect to, let's say, Z. So for that, I need two pieces of notation. First, this is sort of confusingly written as it's just sum. These guys are, possibly 0, but natural numbers, right? 0, 1, 2, 3, 4, 5, right? Of non-negative integers. So it sort of makes sense, right? But it's not the modulus, right? Or it's not any norm or anything. It is this thing. And so then we have, if I want to take a derivative, we just take, let's say, the Z. If I write this, well, what do I mean by that? It's really, I'm just taking the derivative. I'm basically doing the same thing. I have so I think it's right. Yeah. So basically, I take this many derivatives in Z1, this many derivatives in Z2, and so on, right? So so that's why I take this weird notation, right? Just to simplify this. Okay, so now with this, I can of course write down a power series, and let's just do it again. Power series just at 0, right? So I have this. I have a power series in just Z's. I have something like this. I have a power series in Z's and Z bars of real-algebraic. And you have or beta, right? And really what we're going to try to do is, if we have a real analytic, so when we write down a power series, originally it was a power series in X and Y, we write it in terms of Z's and Z bars, so you write it like this. We're going to try to plug in some zeta or something else here. So we have then power series go like this. Now I have a zeta, beta, right? So I have a power series in 2n variables, right? And this is really just going to give you a holomorphic function of 2n variables, right? And the idea is that if this thing converged, right, like if it has a positive radius of convergence, this is gonna have a positive radius of convergence. This is gonna converge in actually a larger set, right? And this converge in a neighborhood of the origin in Rn of R2n, right? And it's gonna converge in a neighborhood of the origin or Cn, right? And this is gonna converge in a neighborhood of the origin in C2n, right? So convergence is not too difficult, just like in the Van variable. That's the same. Then what we need to do is that this is really the unique extension, right? And this is still the same same proof as in one variable, but let me just quickly write it, because it's maybe you've seen a different proof in one variable, or different proof in several variables actually. So we have the following lemma. So this really the idea of complexification. If the complexification wasn't unique, then like this wouldn't really be useful. So suppose that D n cross Cn is the domain. So this is now in this 2n dimensional space. So you have one Cn here. This is going to be my Z. This is going to be my zetas are going to be here. That's another Cn. Right? Then we let D, which is going to be called the diagonal, and that's the set of D's and zetas. And with zeta is bar. Usually people draw it like this. That's a D, right? And let's suppose that D intersect D is some empty. Well, this B really is this is B, right? It's a domain in the in this complexified space. So so that's the setup of B and D, and also suppose that we have F and G are in holomorphic in D. So there are two possible extensions from the diagonal to B, and F equals G on this intersection, B intersect D. Those are domains, open connected set. So then what I get is that F equals G on B. And so on a much larger set. So if they are equal on the diagonal, they're equal everywhere. Right. So that allows us, if we have unique unique extension. Right. So that's really what makes this work. Right. So just like over here, it's a unique holomorphic extension. Now it might be so a little bit more CR geometry. Over here, you can just use the identity term. Over here, the identity term wouldn't work because in higher dimensions, of course, the identity term is a little bit more complicated. This is a totally real submanifold, maximally totally real submanifold, and that's why it works. But it's sort of an easier reason. So the proof is first I just subtract them, so I can just assume one of them is 0. And let's just suppose that we don't need to necessarily suppose it, but what we do is so if we look at if I look at the working and derivative of in a bar of S, right? This one. What do I? So this is F is defined on this set, right? So what do we get by chain rule is actually is the this guy. Right. Now we're saying G is 0, so F is 0 on the diagonal. Right? So we have it over here, this was the derivative of this composition, right? But it's actually the partial derivative with respect to the zeta variable, this composition, right? And so similarly, we get for the z derivative first. So maybe the z derivative is equals to almost like I didn't do anything.
So is the first one psi k bar psi k?
No, so over here, right? So I'm taking f is a function on E, right? By plugging in C bar, I'm parameterizing this this set, right? F is really a function. F is a function of Z and zeta, right? I'm parameterizing this set. So here I'm saying I'm applying this guy to Werthinger's derivative. So this is the Werthinger's derivative. This is an actual holomorphic partial derivative, right? So if I apply it to this composition, right, it's F composed with, you can think of there is this let's say iota or something, which takes Z to Z bar, right? It takes that's basically this idea of treating Z bar separately, or treating just as before as I was writing non-holomorphic functions as functions of Z and Z bar, we're really thinking of functions here, whereas functions of Z are living here. You're really what's over here is really F composite iota, right? That's what I'm doing, right? Whereas over here, that's really the derivative of F, right? This is the derivative of this, whereas this is the derivative with respect to zeta k composite iota.
almost like you can define that like that. I mean,
right. I mean, it's almost nothing, right?
Is defined like that. You treat the second variable as an independent
Right,
variable.
but this thing is defined already, right? So it's not really like I'm not defining it in this way. I have a holomorphic function, so this is well defined, right? This is this right? This guy, 1/2 of and they even live on different spaces, right? I mean, this guy lives on here, right? And I'm really going over here. I'm applying it on C or Cn, right? Whereas these derivatives are in terms of C2n, right? So this people plus. And the same thing here, although here it's maybe a little bit more confusing because maybe if I named the Z something else, but then we get even more letters. So this Z is both this parameter and the thing is parameterizing this coordinate space, right?
So this holomorphicity of F, which is allowing us to like.
Right, it's a holomorphicity of F on B. Right, yeah.
We can use the power series for this inequality, right?
Well, but the thing is that we're trying to get at the power series. How do you get at the power series? You take derivatives, right? We want to relate the Z bar derivatives to the zeta derivatives, right? And it's just
But the only reason I'm making a fuss about this is that people are just really bad at, like, if you have a function defined on the x-axis, they will try to take the y derivative by restricting the function to the. So I mean, you have to be a little bit careful that the derivatives along that are really just.
Right. So here, this is really a function on, right? This is a function. This function is function on Cn, and what I'm applying is this thing, right? So that's perfectly fine. I'm not doing some derivative over here, right? I am doing the derivative over here.
Correct.
Right. Now, this derivative is then, then it's the derivative in the zeta direction. I don't know how to draw it.
But it's along the diagonal, right? So
right.
they're different, which is why this is a non-trivial.
But it's right, yeah. I mean, it is a non-trivial statement. Like it's not just a trivial, right? I mean, we really are either talking. We're really starting with a function on here. We say, suppose that we could extend it to a function on B, right? And what do I mean by that is that we would embed the Cn onto this D. So we're thinking of this Cn. Essentially, what we're doing is we're taking the Cn, we're dropping all complex structure on it, and we're embedding it as this maximally totally real subset of this C2n, right? Why are we dropping all the complex structure on it? Well, because we're starting with something that's real analytic, right? So so we drop all the complex structure, and that's why we're getting, this thing is there, it's fine, because we're allowing Z bars now, right? But it's so it's maybe like a different. So over here, there's none of that, right? You are really looking at the real line, and you're plugging that in. Now that would be, there's also a possibility for the complexification, but you get a different complexification, right? You're then living in a different space. Does that make some sense at least? So, for example, in over here, if I guess it's a slightly different thing because we're taking this F is really living on.
So maybe the point is that you're looking at the function F of Z, comma zeta of Z, where zeta of Z is equal to Z bar.
Right.
And then
Exactly.
you apply the chain rule to that.
Right.
Just to have clear proof of this.
Right.
F of Z, that's your thing, right? F of Z, comma zeta of Z, where zeta of Z is Z bar.
Right. So
when you apply the chain rule, you'll get
this because right. So what do you get? You get the derivative applied to first you're applying it to
Z.
the Z, but you're taking the Z bar derivative.
So that doesn't show up. Then you take derivative with respect to zeta, and the derivative of zeta with respect to c bar is 1.
Right.
Because zeta of z is c bar.
Right, exactly. So it is precisely chain rule. So it's not completely trivial, right? It looks trivial, but it's not.
Just a tiny thing. It should be zeta of z bar. You said zeta of z is z bar.
No,
right?
but a priori of function is just, I mean, in his notation, yes, but not in my notation.
Yeah,
That's
that's exactly what I'm saying. So I think this particular computation is exactly getting at the heart of the notational issue, right?
No, but I don't see a problem with calling it zeta of z.
So as long as you
Yeah.
okay with the notation, but if you want to keep track of holomorphicity and anti-holomorphicity, zeta would just be a smooth function.
Right. I mean, well, I mean, zeta of z. I mean, you're basically trying to think of it as a function on. I guess it's just a different way of
Writing it.
thinking of this inclusion, right? So thinking of z as a function of z and zeta as a function of z, right? Right. So that makes sense.
No, this is not for me. I'm just saying that students
No,
get
no.
a lot of.
Yeah.
They just take derivatives wherever they see, and this is just something that's important that they understand.
Right. I mean, you have to you have to really think about this computation. Make sure it's not just formal nonsense, right? And it is really over here. It's maybe a little bit. So this might be a little bit more confusing than this because this thing, the way it is defined, is this, right? So this makes more sense. Over here, this thing and the derivative over here are distinct things. This is the Worthing derivative in Cn. This guy is the holomorphic partial derivative in C2n for the case component. Right. That's just the thing. Does that make sense? So, so yeah, I mean it is. Probably in doing these sort of computations is actually keeping track of what's going on, right? But once you get the hang of this, it just sort of goes automatically. Anyway, so we have those two derivatives are 0, and it's really you get every other derivative in the same way. So if I have if I'm going to get I look at any any derivative in maybe I can write it out that way. So beta of which is, I mean, this thing, the whole point is that this thing is identical to 0, right? Over here, right?
So, why are they 0 between why these two derivatives you're saying they are 0?
Because so f is equal to g on here.
Yes.
So f is equal to g on here, and we're assuming without longitudinality that g is 0. So we're basically assuming without longitudinality that f is 0 on D, right? So it's 0 in here, and we're trying to show that it's actually 0 everywhere else. Oh, so we get that because this is identical. This is f composed with iota, right? So this is just identical to 0, right? So we get that this is 0, but then by chain rule, it's just here. Right, we're still doing it on the diagonal, right? So we're not necessarily getting that, or not yet at least, that those derivatives are 0 anywhere else but on here. But we don't really now care about this thing. We care about this thing. This tells us that if I take so this is holomorphic, right? So I can let's just suppose that we're at the origin. Let's suppose that this was the origin. If we write down the power series for this holomorphic function, right? F, right, of z and zeta, right? It's right. let's say near 0, f of z zeta is equal to alpha theta beta, right? What does it say? This says that all of these guys are 0, right? That's how we compute the coefficients with the state theorems, right? Right? Which means that that now we get the function is 0, identical to 0 in all neighborhood, right? Now that's B is a domain, so therefore we get the function is 0, 0 everywhere on B, right? So so this is a bit tricky, right? To think about this, and again, it really is this. If we're writing things in terms of z and z bar, we are thinking of really not here. That would be when you're thinking of it as a function of z, maybe not holomorphic. But if you want to think of it as a function of z and z bar, you really are applying this embedding of Cn onto the C2n.
Right. I wouldn't think of zeta as a function of C and Z bar, because then zeta would already be living on the diagonal, right? I mean, there is zeta living. If I write this map,
So I would think of zeta as a function from I guess C and C.
then it's not living on that map. Then is it living on this, or is it?
It would be the vertical.
The vertical is.
Well, you can think of like if z is 0, right?
Right.
Or you can think of it as the coordinate plane, right? But I mean, there's going to be lots of ways to think about
the
this.
question whether you want to look at zeta as a if you see as a function, then that's it. If you want B as the graph, right?
That's what I'm saying. So then zeta is already a function of z and z bar.
Right.
Then what is the domain of zeta? Is it not already the diagonal?
No. So then the diagonal would be the graph, right? Because
So
then
then it's just a function of.
Right, but basically, so you know, maybe this I think always comes up whenever when speaking some like different geometry or like vector calculus, right? I get vector calculus too. Like that's where it's most confusing, right? Is that when you're taking derivatives, are you really taking derivatives with respect to the variables or some function? Right? So you can either make up new names for the functions or think of zeta as a function, even though it's a variable.
Yeah.
So I guess I guess your zeta is the second component of iota.
Right, exactly.
So you can think of
That's what I mean.
iota sub 2 is your zeta, and z is iota sub 1. Okay, so then this means that if I make 0 like this.
just go back to Cooley's point. This took me a long time to sort of sort out because this is super confusing, right? So either you should be very comfortable with already, or it should be super confusing. If you're not in any of these camps, then you should think hard about what just happened.
Right. I mean, if it seems like nothing happens, then yeah, then you're there's something wrong.
Then there's trouble, right?
Yeah. Right. If you don't see the chain rule, if like these two
This
objects
should
are
make you
not.
uncomfortable. That's
Yeah,
that
exactly,
sentence
right,
should make you
exactly.
uncomfortable. That's all.
So I was thinking that if it is a holomorphic function on this domain T, you
Yep.
already have a power series function, right? You already have a power series function near and equal.
We already so
Already have a power series expansion.
right. Yeah, exactly.
So why not work with the power series directly without going?
Well, then you have to prove. So if I start with a power series, right? So that's really what we would do. Like if so this is going to the other direction. This is proving the uniqueness, right? I mean, to prove uniqueness in this sort of
You mean the uniqueness of the power series?
right, but it's not the uniqueness of the power series. It's the uniqueness of the extension. It's really so if this D was not maximally totally real, if it's right, I mean, if I had if it was maybe instead of this D, if it was really this, and I had a function of just Z, then there's many ways to extend it into the C2n space using power series or any other ways, right? So the point is that this is really the only way, right? It's essentially proving the identity term for maximally totally real, at least a hyperplane, right? That's the thing that's needed here, right? Because if you start with a parser, is just plug in. Well, how do you know that I'm not gonna get some other holomorphic function which happens to equal this, right?
So he's saying that F and G are already the extensions, right? They're
Yeah,
already
exactly.
the extensions, and he's saying take power series of those.
No, I think
What do you say?
I think you're sort of starting. So if you start with a
Wait, are we talking about this left? We're talking about this left, right?
so I think okay, so
we take G is a already homomorphic function,
right.
Cn cross Cn.
Right, but we only know those holomorphic functions on a small set.
No, F and G are given to be holomorphic.
Right, but we only know that they're equal.
Yes.
Oh, that's why.
We will use the equality later, but derivative will differentiate on this power series.
Right, but the thing is that the derivatives in Z and zeta bar are not tangent to D. They're Z and zeta. So you cannot just take, to prove that this derivative, let's say it's is zero, well, you have to differentiate this thing along something that's not tangent to the set D.
Yeah.
Does that make sense?
Yeah. You have to use the embedding, otherwise you cannot.
Right, exactly. We're using that embedding, right? So it's only on that set that we have zero, right? We have to somehow use that, right? So we can differentiate in Z or Z bar or X and Y, but we cannot. Well, we can differentiate. We just don't know how to compute this a priori without doing this. Does that make sense? So yeah. So we only so yes, we could start with, well, we are essentially starting with the power series, right? Saying it is the there. So it is the power series. We just have to figure out how to show that these things are zero, right? We are something, right? Okay. Does it? Yeah, I mean, this is it's one of these things that
is more complicated than necessary.
No, but I think it's good, because this comes into all of this, and it's key to the extension, right? So it's really key to this idea that that it makes sense to do this sort of this sort of complexification, right? Because just because I do some sort of extension, why is it unique? Why it makes any sense whatsoever, right? So, all right. So now if I have a real analytic function, I can at least I can think of it. If I have a real analytic function on Cn, I can think of it as the Cn. I can really identify the Cn with the D, right, with the diagonal, and then I can do this extension and get a function in C2n and get it, and it's unique, right? Now the downside is, of course, is that you don't get necessarily, like if I have a holomorphic function in some set over here, right? I'm not gonna get the extension is not gonna work in a set like this, right? The extension might work in a set like this, right? I cannot completely move the Z's and Z bars arbitrarily. It's not necessarily going to converge. That point is already over here, like with this sort of complexification. It's the same idea. If I look at 1 over, so maybe, okay. It's just a little bit more, or maybe I can do it in this setting. So suppose that I have a real analytic function. Let's just suppose that I'm having one variable, and so Z bar, and it's 1 over 1 plus maybe epsilon. Right. I mean, this is for positive epsilon, right? This is a perfectly nice real analytic function on the entire C, right? But there is no holomorphic function on C to N, right? Because that restricts to this thing. Right? There's a holomorphic function on the smaller domain, right? Because if I want to complexify, I would have this thing, right? That would be the complexification. But now this thing has zeros, right? This is, I'm going to be dividing by 0 here, right? So it's not going to. So you can't always, you know, there might be. So over here, what's happening? There are these complex hypersurfaces, but they just somewhere here they don't touch D, right? But I cannot define the extension everywhere because the extension will go bad. And when epsilon is small, these are closer and closer to D, right? And so there's for real analytic functions, of course, like there's no way to sort of figure out just from the function values in an easy way how far the thing will converge, right? So you have to be much more careful. Okay. As long as you can, you know, whatever you're saying can work in a small enough neighborhood, everything is good. So as long as, you know, what you're trying to do, you can always put for a small enough neighborhood into your statement. You're good.
It will be in the neighborhood of P.
Yeah, the B would be smaller. Yeah. So, yeah, neighborhood of D. Yeah. Let's see. Right, so now we want to do the extension to here. I have a real analytic hypersurface. I have a real analytic CR CR function, and I want it to be at least locally in a sufficiently small neighborhood, restriction of all holomorphic function. So for this, what we have to do, so first we write our hypersurface like this. Okay. Everything real analytic, right? So P omega, right? And we have we're at the origin, and this thing is tangent. Measure NW equals 0. Now you want to start doing complexification of some function. So before we get to any function, let's complexify this thing. So what I could do is, I mean, everything is real analytic. So these are real analytic functions, right? So I have, I write them just in terms of C's and G bars. And W bars. All right. Now I do this complexification. I start with, if I get near any point, I look at the power series in terms of Z bar, W bar, and then I can, by using that lemma, essentially, I can just now think of uniquely as I have a holomorphic an extension. It's complexification. Right? It's called complexification. If you read John D'Angelo's book, this is the version 2 complexification or something like that, because the original one was the X, that's version 1. It's slightly different. So, all right. So we have this. So now we can think of basically just plugging in those zetas over here, right?
Sorry, what was the version 1?
So the version 1 is if we're starting with something on Rn and we're extending to Cn. The version 2 is we're starting with Cn, and instead of thinking of it as R2n, we're thinking of it as, you know, using the Z's and the Z bars, right? So it's a slightly different complexification. It only works if you're starting from Cn, right? The other one, I could start with, let's say, R, right, which is odd dimensional, so it doesn't have any complex structure, right?
From R you would get 2 complex, but here you would actually end up getting 4 complex.
Well, no, for R, like you cannot do the second version, right? Because it doesn't make sense.
No, I'm saying here,
Yep.
you would replace Z bar also and W bar also.
Yeah.
with
So
complex
here, I mean, I'm starting in Cn, and I'm going to get into C2n, right? If I think of
Right.
Z bar and W bar as separate variables, right?
Yeah.
Uh,
No.
No, 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 no.
R4, I mean,
So
from
it would be
R4
R4n.
First one is
Yes.
R into R2.
Yes, and the second one is Cn to C2.
But the thing is, like the idea is that we're starting with something on Cn, and we have real objects there, the real and holomorphic objects, and we're trying to figure out like the interaction between them, right? And what we do is we move to C2n, where there are no real objects left. It's all holomorphic objects, and the things that used to be holomorphic objects are well, still holomorphic objects, but now they don't depend on some of the variables, right? Originally holomorphic function is now a holomorphic function which doesn't depend on zetas, right?
Mhm.
And an anti-holomorphic function is a function that doesn't depend on z but can depend on zetas, right? Does that make sense?
So we can compose this process and go from Ra to R2 and then make a holomorphic function and then complexify it to that.
Maybe I'm not.
You said if you start with a holomorphic function Cn,
Right.
and complexify and get.
Well, I mean, if everything was holomorphic, you wouldn't need to complexify, right? But it's really but yeah, but you can think of, if I have a holomorphic function in Cn, so it's a holomorphic function of n complex variables, and if I complexify that, I think of it as a function on C2n that just happens to not depend on the last n variables. Does that make sense? If I want to sort of work with real objects as well, right?
So the first complexification versus the second, if we were to do that on C, then it's like if you take the variable Z, then it's like treating X and Y as 2 complex variables versus treating Z and Z bar as 2 complex variables.
Right.
Right. So on the same thing you can do. It makes sense to talk about the 2 complexification on the same space.
Right.
And so on C it's about which 2 you want to treat as
Right.
independent variables.
Right.
Right.
But the thing is it's doing the complexification with the X and Y is not actually that useful.
Yes, for the purpose of exactly.
Right. Because the thing is it's much harder. So that's basically would be, taking this operator, you'd have to sort of worry about like what does it mean to have a holomorphic function then, right? And it would be taking this operator, thinking of it as this just being holomorphic. These would suddenly be the holomorphic partial derivatives, and you have something that satisfies this being 0, right? Which is much more complicated than saying this thing just does not depend on the variable. Does it make sense? It's sort of, I guess, it's the same like if you're solving the one-dimensional wave equation, right? You change coordinates to make things that depend only on one or the other variable, right? And so solving it in the original coordinates is hard. Solving it in the what are they called? Characteristic coordinates is easy, right? So that's basically what we're doing. That's actually sort of exactly what we're doing. So, but we're not interested in the wave equation. But that would be the analog. It's just that with the wave equation, it's basically the same thing without the eyes, plus and minus, but without the eyes. So if you put the eyes in there, it's the same idea. All right. So we have this. So now we can think of. This is clearly easy to complexify. Okay, so you complexify it in some neighborhood of the origin. You write down the power series. And now I can plug in Z bar as a separate variable, right? It doesn't have to be Z bar, it could be just a separate variable. So what I can do now is I can look at this and I can apply the holomorphic implicit function term and solve for, let's say, W bar, right? Let me make sure I'm using this the right notation. So I'm using Q, right? So I'm going to use implicit function term, right? I mean, I'm writing the same set, but I'm writing it as W bar is Q Z bar W. Right? I find a holomorphic function Q using the implicit function term, such that this is true, right? It's no longer a real equation, right? It's like you can see the realness by if I bar this, you know, if I have this, I also have this. This thing for NW bar, so these things are not always equal, right? I mean, these things are you know, these define n, right? These equations, right? I can just think of one, but I mean both are true. One is,
That's to understand it properly. We need that because we
in C2n, yeah, so Cn cross Cn, yeah. So basically, so I first think of everything as holomorphic, right? So I you know, there's no longer anything real, basically. That's so then you can freely use you know, everything you know, about holomorphic functions. And that's really the whole idea here, right? And that's the thing that you can do with real analytic things that you cannot do with smooth things. There's just no way. None of this makes any sense if everything is smooth, right? I mean, formally it makes sense, but then yeah, non-convergent power series. You can actually plug things in. Right? Anyway, so we have this now, the realness. It's not quickly necessary, but to see that this is really not a different equation. But I mean, this the way to think of Q bar would be really is barring all the coefficients in the power series, right? And I have to plug in the Z bar. I mean, think of a power series here, and if I bar everything, the Z's become Z bars and so on, right? The realness of that equation is actually given by, I could write this in two ways. But so this is actually identical. It's not just on M. Right? I really have solved for W or W bar. Right? Now again, treating W and W bar separately. Right? So if I want to think of it as solving for.
there should be a W bar there, right? U bar of Z bar, Z W bar.
W. Right. This is not strictly necessary, but it sort of shows that this is not really a separate equation. If you just wrote down a random equation, it would come from if I intersect this with on the diagonal, I'm supposed to get a hypersurface. You wouldn't get a hypersurface unless you had this equation, basically.
If you get confused, what's the point of the Hofstadter equation?
Just to show that this was actually a real equation. So like if you don't see it, don't worry about it because we won't use it. Okay. So but it's but unless you have this, you're not gonna because normally if I look at if I write down a holomorphic equation, right, it's not going to necessarily hit D in a hypersurface, right? If I look at the zero set of a holomorphic equation C2n, the way it intersects D, right, it's something, right? This says that it's actually a nice hypersurface. It was a real equation to begin with, right? If it's don't worry about it too much because it's not that important. Because we're starting on that, so we don't have to go back. So it's then we also from those facts, so we don't quite get that this is this vanishes up to second order. Vanishes up to second order in Z and Z bar, but not necessarily W. Actually, it can't. So this is still we get Q at 0, 0, 0 is 0. We get that, but it's the and vanish, but not the W derivative. You're not going to get that because look at it over here. Right? I mean, essentially, you could if you'd write this down as a in like suppose it was actually a polynomial, you could actually do it formally, right? Well, maybe.
I mean, let's say it did not depend on the real part of W. Then what would be the next step? We would just send W to the other side. I mean, if it did not depend on the real part of W or phi.
Right.
Then
Yeah. Then it would be exactly. So for example, if I'm starting with something like imaginary W equals mod Z squared, that's the guy up here. What is the Q? Well, I guess I would have sorry for W bar. I'm gonna get the minus sign wrong, right? So minus 2i bar plus right, plus up. Right? So this is the Q then, right? So you can see that, yeah, I'm not gonna get the W derivative is not gonna be 0, right?
Oh, okay, now I get it. There's a Q bar of W bar. I was not seeing the Q bar.
Yeah.
Right, and so but yeah.
I thought you just got rid of W. I'm like, this is
No.
like magic.
No. Yeah, there's Q bars, so it's basically that the bar is not really giving you anything new, but that you started with real equations. Right? Anyway, doesn't really matter. This is the key thing, and the fact that this basically this works even if I treat Z and Z bar separately. Works. I mean, it's some object, right? But when Z bar is actually Z bar, then I'm getting that set. And W bar is W bar, right? So, all right. So we have this. Now, from this equation, we can also figure out a basis. Get through it. Figure out a basis for the CR vector fields, right? Well, so now if I want to have some, I could think of it as maybe minus sign here. I could think of things that kill this, and they should also kill this, but they'll do that automatically. So, but they're supposed to kill this, the vector fields, and I want them to be CR vector fields, so I want in Z bar and W bar, right? And so there's going to be, if I have, if it was in Cn, right? So there's n minus 1 Z's, right? So I'm going to get n minus 1 vector fields, and the vector fields, let me write them. I guess it's slightly different, putting k here, but that's not the point. That's the kth vector, and these are actually vector fields, right? So if I differentiate with respect to just would get for k plus or k right? I look at this, right? That's my those are going to be my vector fields, and those will kill this thing, right? They'll also kill this thing, right? If I subtract these, that will work well. But it's so these are tangent to. So now they're written in even in the way that we were doing it before, right? These are just if I just think of Z bar as really being Z bar and W bar being W bar, then I get precisely these complexified, 0, 1 vector fields, right? And so now I can talk about CR functions, right? The things that are killed by this, right? So this is a nice basis of my CR vector fields. It will be a basis near 0, right? Where everything is local, right? So now we get to can write down Segre's theorem. And sometimes it's not, in a lot of places it's not named. I remember I was in this conference in Brazil, and we did this generalization of Segre's theorem, citing the Segre's theorem, and Trebs was there, and he said, "Oh, you don't have to cite Segre, he was a Nazi." Which is actually true. He was Italian, so he was fascist, right? So he was first he was an anti-fascist communist when he was younger. Then the fascists came to power, so it became much more convenient to be a fascist. And then after the war, he tried to become an anti-fascist, but by that time nobody believed him. Like maybe one switching was like if you switch twice, okay, but then nobody.
In which phase did he prove this theorem? Is the important question.
I think this is right on the border. I think like 30 something, like early 30s. Oh no. So Italy fell. He was fighting for the earth since 20.
Yeah,
so he was already a fascist.
Okay.
Who cares, right? It's just a thing. The term is not responsible for the. and the thing is, like, he probably wasn't really believing fascism. Just like he wasn't a believing communist, if he was willing to switch from one to the other. All right, so here we have if I'll write it as a CR manifold, but we're only going to do the hypersurface thing, but it works in any dimension for any CR manifold. So if M is C omega, so real-algebraic CR manifold, submanifold, I guess. N and F is real-algebraic function. And F is holomorphic. Holomorphic function of neighborhood of M, right? So, and we're gonna only hypersurface. That's the only thing we need, and it's the same idea. It's just more annoying notation. You can do this sort of thing for if you have a higher dimension, you just have more W's. All right. I just if you thought the previous thing was cheating, right? The complexification, and then this is really cheating. The proof of this. So,
Just a small question. Do you need generic CR
if it's generic, it's unique. If it's not generic, it's not going to be unique. But yeah, you could just assume generic for all practical purposes. Right? But yeah. But we're only going to do hypersurfaces, so those are generic. So generic, well, for maybe smooth, it's slightly more complicated. For real-algebraic, it just means you're not contained in a lower dimensional complex manifold. It's somehow generic just means that you're sort of in as high of a, for real-algebraic. For smooth, it's a bit more complicated. It's a condition on the CR vector fields, right? And it's a terrible naming. Because it is a generic condition, but it's not like, if you say generic manifold, like, do you mean a generic manifold or a generic manifold? So yeah, but somehow it's stuck. All right. Yeah, sure.
The restriction we have, so the domain where the extension will be there will depend on it, right?
Oh yeah. The domain where this, so it just says nothing about where F is defined. Like it's just like before, it's hard to like from the real only knowing the real line, you cannot know how far things will extend.
1 by epsilon square plus mod square.
Right. I mean, it's exactly the thing. Right? It's you cannot see how far you can take it. That depends on the function. Yeah. It's very it's you have to compute some where the series converges, right? So however you whatever is your favorite way of doing that, but nothing on M will tell you, right? You have to know F. All right, so take yeah. So it's enough to do it locally, right? So we're gonna do it locally, right? So we work, right? And we're gonna have this guy, right? So we're gonna do everything near 0 locally, right? So take any extension F E or W. I have a real-algebraic function that's only defined on M, right? But I can take an arbitrary real-algebraic extension to, I can basically just take some set of real-algebraic coordinates and just, write it down into any extension whatsoever. This is not going to be the right thing, right? This is going to have definitely Z's and G bars, right? But now, how would it work if it was just, if we were extending from the real line, right? So we had that's where W bar is equal to W, right? So what we could do is if we extended, if we were just on the real line, if it were just in C, there was no Z's, right? And we have a function, we write it in terms of Z and so W and W bar, right? And we want to extend it, we can just replace W bar with W, and we have a holomorphic function, right? So that's what we're going to do, right? So I think and you have to really sort of think about what's happening, because the W bar is really independent of W, right? So now now there's no more W bar. It's great. We have a holomorphic function in W, not yet in the Z's, right? But now we apply. So something that we haven't used yet is that it's a CR function. That's what we have to use. We have this nice basis of the CR vector fields, right? So we apply the CR vector fields, and we have that on M. Not elsewhere, but on M, we have 0 because it's a CR function. So if I hit it with x bar k, it's 0, right? So maybe this thing, right? Whatever this function is, right? Instead of giving it a name, it's going to say this thing. Well, what do I get? Right? So I get, which is actually the same thing as if I had F because it's tangential and this is defining the manifold. So I would get the same thing. So I get F df d. My brain's not working anymore, so I really have to go from this. Plus dq d bar k d f. Right? So this would be applying this guy to F, right?
You're trying to give it to left.
Yeah, originally, but I'm on M, so it's it's applying it to here and plugging this thing into it, like same thing. But now I get this thing at 0. So
the over series and show the coefficient where it is analysis is longer zero. In over series,
Right.
all the coefficient was z bar analysis those are zero.
So so we have to you know, because we have to get there. Now I'm really you know, feeling like my brain's not working. Right. So here we should have this. Right. Yeah. We don't have to, you know, compute all the bar series, right? Why do we get this? So this is 0 at 0, but maybe not 0 elsewhere. But this thing, you know, we have this guy, you know, doesn't depend on, you know, on W bar, right? And again, you know, the way to think of it is to think of it in, you know, in the C2N, right? Everything is holomorphic, right? And so, so this guy is 0, right? There's no W bar, right? So therefore, I get this. So I get that these guys are 0, okay, on M, right? But now we have, so for any fixed, right? So for a fixed Z and Z bar, really, if I'm thinking of it, and Z bar, which is equal to Z bar, right? I am looking at the, you know, on the diagonal. What we get is this function which is holomorphic in W. If I differentiate, I get again a holomorphic function. I'm differentiating in terms of Z bar, right? I get a holomorphic function in W, right? Maybe I don't yet know there's that this thing is 0, but it's at least holomorphic in W, right? And it's, you know, for a fixed Z in the W plane, there's a whole curve, right? So for any fixed Z, right? If I fix Z, you can see it here, right? The same set over here, right? I mean, I had to get a whole curve, right? Maybe not the real line. I mean, if this was 0, I get the real line, but I might get some different, right? So I just restrict my, you know, I look at my hypersurface, you know, how it is above a fixed Z, right? And it has to be a curve, right? And the holomorphic function is 0 on a curve in C, right? So by identity term, it's 0 in a neighborhood, right? So it's maybe should draw that, right? So first, you know, this is imaginary of W equals speed of D or real W, right? It's some curve, right? Some one-dimensional curve, right? So by identity, I get that df d z bar k is just identically 0, right? Everywhere, or at least in a neighborhood of the origin, right? It's 0 here, and this was for any z, so I get it everywhere, right? Well, that means I'm done, right? This thing, this expression, right? My f of z w, I can write it as this. Write the z bar in there, but it's not there, right? In some sense, right? I know that there's no z bar here, right? And, you know, if I do this formally, if I plug into the power series, basically the z bars would all cancel out, right? Which is what this is saying. This is for all k. I'm getting that this expression does not depend on any of the z bars. So here's my holomorphic function, right? And so didn't quite get to right. A little stuck on this thing, but this should feel like cheating, right? Because this is because it is, right? We're really sort of moving formal things, you know, around, and you really have to sort of, where we started with the complexification, you really have to sort of, understand, what's going on there to understand this, right? And the difference between thinking, in the CN and thinking in the C2A, right? That's, here in a small neighborhood of the Earth, right? But once, once you get past this sort of, being able to go back and forth between z bar being the conjugate of z or being a separate variable, right? And so being able to go from the diagonal to a neighborhood of the diagonal, right? That's basically where this is, and we're really starting with things just on the diagonal and trying to write everything in terms of things in a neighborhood of the diagonal. All right. So.
What is that for a fixed z and?
Oh, here?
No. Fixed z.
Z bar into the Z bar.
Oh, Z bar is Z bar. So Z bar is Z, the whole thing bar.
Okay,
Right.
so
So I'm really thinking I'm at a fixed Z, right? In the I'm really back here, right? I'm not thinking in the I'm setting because that's not yet necessarily going to be everywhere, right?
Yeah.
It's going to end up being everywhere because there's no Z bar. But
so the left Z bar is the independent coordinate.
yeah,
The right Z bar is you take the value of Z and then you take the conjugate and you
Right.
plug it into the
so
independent variable Z
I'm
bar.
saying that Z is fixed and Z bar is the conjugate of Z, right?
Yeah.
Right. So I'm at that point. I'm really at Z bar and not at some random Z bar or Z bar or something else.
The left one is the independent.
Variable, and
Yeah.
you're plugging the correct conjugate value into that independent variable.
That is the set where they're both equal.
That's right. You're on the
Yeah,
now
I'm
you're
just
on the diagonal.
fixing, I'm just saying that we are at one of these things because then I know what my set is.
Yeah.
Right. And I know that I have this on M, and so I know what it what that looks like over there. Right. It's just some curve, and so I have a holomorphic function which is 0 on a curve. And so it is, it's a tricky proof, but it's basically it's the basis of so we're going to get to this Segre variety business hopefully for Levi-flats, and so this is basically the idea is that you can think of we have these real objects and you want to really think of the Z and Z bar separately, and you can think of so you can either move along the diagonal or you can move just in the Z and the W coordinates in the without moving there, right? So, all right. I don't think I'm gonna get all that much further. We're almost we can basically prove this Cartan's term like this flattening, but not in 3 minutes. So, but basically the idea is going to be this, right? So I'm just going to say the idea. We're going to do it next time.
Okay.
Reverse camera. Oh, there it is. So it's basically what we're going to do is if we have a Levi-flat, right? So real analytic Levi-flat. We use that characterization of the Levy form as a projection into the bad direction, and basically, something is Levi-flat. If that thing is just 0, if you're just getting, it basically just means that that you get that. Basically, just means that that we'll get that T01 M 0 that's invalid on the flat. One way to say that it's Linux flat is an involutive this distribution. It's complexified, but you could always just if you restrict back to the real tangent, real tangent space, you're gonna get an involutive guy there. So you can apply Frobenius, you're gonna get a foliation out of it, right? You're gonna get a real analytic foliation because everything's real analytic. I mean, if it's smooth, you get a smooth foliation, but then we'd be stuck, then we wouldn't know what to do next. But if it's a real analytic foliation, you're gonna get a real analytic foliation, right? Now, so you saw that for a foliation, you had different ways of thinking about it. So think about it as using a submersion, right? It's a co-dimension one, so the submersion is just a single real value function, right? So you get a real value function which is going to be constant on these leaves, right? Now if it's constant on these leaves, it's constant along vector fields. I guess I wrote it. Normally I wrote the one zero. It doesn't matter, but it's going to be it vanishes along this entire thing, so it vanishes along these guys. So therefore, that submersion is going to be a CR function. Now, the CR function, that's going to be my W, it's going to be my real W, right? And I use Segre, this thing, to take that thing, that CR function, we extend it, so and then we get a holomorphic function. That's our W, right? That's our coordinate W, right? And that's how we get the normalization, right? So okay, so we'll do that next time.